experts, which means they've scheduled the best talks for this session. So thank you for being here. We have 3 talks. The first talk will be given by Sabine Laurent on placement of loading stations for electric vehicles.
All right, so let's see what the motivation for our problem is. So we're talking about route planning, which is the problem I guess you all know. So you want to go from A to B, and normally what you do is you ask for the quickest route or something. Okay, and if you have a conventional car, you're normally oblivious to gas stations, because what you do is, well, you drive, and if your charging level or your fuel level approaches 0, maybe plus some safety margin, depends on how risky you like to live, you have to look around, and then normally there is just some gas station around. Okay, so maybe directly on the route, maybe a bit off, but kind of close, so you can just go there and reach the target. And now our topic of interest is electric vehicles, and here this observation is not true in most cases. So what happens is, if you use the same approach, just drive along, and if your fuel, your charge level approaches 0, you look around, well, there's nothing. So you just get stranded there. Okay, so you're stuck. Which means normally you have to really plan ahead to use loading stations that are there. And maybe there's not even with all the planning you can do, there won't be any loading stations around, so you won't be able to reach the target at all, no matter what you do. And to overcome this problem, 2 solutions have been proposed in the past, which are kind of 2 extreme scenarios, as we will see in a second. So the first one is the so-called reachability cover, which has the idea of building a very small backbone of loading stations that's where you're guaranteed to go from anywhere to anywhere. Okay, so you can reach everything. The problem here is that there's no guarantee how long the route will be. Okay, so it might be that you go from Berlin to London, but you go via this one. So, okay, so an extreme scenario. Okay, this doesn't seem to be really convenient for a EV driver, and does not convince people to change to EVs. And then there was this other extreme solution proposed with it, which is just make every shortest path really drivable with an EV. Okay, so you can do that. You can place a lot of loading stations on every shortest path there is. Then you're fine, and then your EV doesn't need to have a special navigation system which is aware of loading stations, but you just use the normal route planning systems. But the problem here is you need a really huge set of loading stations to guarantee that. So a new idea of our problem which we propose is the so-called detour cover, which is we still want to stick to the shortest paths as much as possible, but then we are allowed to leave the shortest path, use some bounded detour, which we describe as parameter D, and then go back to the shortest route and so on, for which we hope that the induced detour overall is pretty small, and we still can use route planning tools which are available for conventional cars. And if you look at this parameter D, we see that our new problem kind of subsumes the previous work, because with D being equal to 0, we have basically this shortest path cover problem, and with D approaching infinity, we have this reachability problem, and you can have huge detours. So let's have a look at how to solve this problem. Our idea was to formulate this as an instance of the hitting cell problem. And so the idea is to have these paths. We have these loading stations which make paths feasible. So there's some infeasible paths where you run out of energy, and we want to place loading stations that's where we become feasible. And a naive formulation would be to extract all paths which are longer than B, with B describing how far you can go with your electric vehicle, so that's kind of how large the battery is. And we could determine all of these loading station positions per path, and if there would be a real loading station, you could go on this path. And then we just determine the smallest set. Okay, this looks beautiful and clean, and it's all wrong, because it does not guarantee global feasibility. If you look at this picture, right here, you see every subpath, if you have a battery load of 100, every subpath has a loading station, every subpath longer than 100 has a loading station on it. But you cannot drive from S to T, and the reason is that if you use this first loading station, you can do that. So you drive here, you have a battery load of 10 remaining, go to the loading station, reload to 100 again, go here, you have a battery load of 90 remaining, but the remaining path has a cost of 95. Okay? You would like to use both of these loading stations, but the problem is you cannot reach the second one without using the first one, and you cannot take them both, because this entry vertex of this loading station is after the place where you would have to leave the shortest path to go to the other one. Okay, so this does not guarantee global feasibility. What does is the following, so we changed the hitting set formulation a little bit. we don't hit all paths longer than B, but B minus 2 times the possible detour. Then we go to the same, and we can now prove that this guarantees global feasibility. You can see here, now we can take any of shortest paths which there is in a network. We look at a prefix of length B minus 2D. We know there has to be a loading station which we can reach because this is kind of how we formulated the problem. And now we know that at this point we have a battery load of at least B minus D because here we fully recharge, and then this thing here is of course bounded by D. Okay? Now we look at the next part, starting from here, also of length B minus 2D, and we look at this loading station here. We know that we can reach this loading station for sure, because this path here has length at most B minus 2D, and this part here has length at most D, so if we sum it up, this is at most B minus D, and this is the battery load we have. Okay, so in this approach, we can guarantee global feasibility. It looks like the problem is solved, because now we can use the whole machinery which is available for hitting set problems, like the greedy algorithm, and now we have a solution. Okay, so this sounds good in theory, but we'll see it won't work in practice. And the reason for that is the following. So we call this the real greedy approach explicit thickening, because what we do is we have all these shortest paths where the electric vehicle would run out of energy, and we thicken them by aggregating the whole set of loading stations. Each of them would make the path feasible. Okay, so we get these kinds of sets. So which means we have some point on the shortest path, and we can drive to the loading station, and then we can drive back, maybe to the same point, maybe to another one, and the total induced detour is at most D. And we can compute these sets very elegantly. We just need one run of Dijkstra initialized 0 for all the points on the shortest path to compute the smallest label to get to the loading station, and then another Dijkstra run to go back to the shortest path. So we only need 2 Dijkstra runs, and we're at most D away from the shortest path, so this can be done very efficiently. The problem is computing all shortest paths in the network and then storing these sets is super quadratic in the number of nodes in the network, so this is absolutely infeasible. So if you want to store only shortest paths, this might be feasible because there are nice compression techniques, but now we have these potato-shaped sets of loading stations around these shortest paths, and storing them is kind of not easy. So our idea was, maybe we don't have to store them. We can compute them efficiently. Maybe it's enough to compute them on demand. Okay, so what we have to make sure to still allow greedy to work is that he knows how many sets are hit by each vertex, by each possible loading station position. So we do the following thing. We initialize a counter per vertex with 0, and then we go through the sets of our shortest paths on which DB runs out of energy, and for each of those, we compute this loading station set on demand. Okay, we can do this, and then we increase the counter for every vertex in there, so we get the true counters which we would like to have for the greedy algorithm for the hitting set problem. What we can do then is just proceed like normally for greedy. We select the best hitter, the one which hits most of the paths, add it to the loading station sets, and then we need to delete all of the paths which are hit, which means we make this whole thing again. We go through our sets, compute these thickened paths, and if the best hitter is contained in there, we just delete it, like the one in the middle here. Okay, this would be deleted after this round. Maybe just do it again and again until our set's end. This computes the very same solution as this explicit thickening thing. Okay, we computed the true counters, in significantly less space because we don't have to store this whole set on at once, but only one per path. But the runtime is still pretty huge. You can imagine you have to go through all of these paths, which are quadratic in a number of nodes, and then you have to do this thickening process. It's very slow. So we go on and think about heuristics. Okay, so now we have an approximation guarantee. Greedy assures us that we are not more than a factor of log n away from the optimal solution, but maybe it's just not efficient enough. So we look at what can be done if we don't have this approximation guarantee anymore necessarily. Okay, so first heuristic which we thought about is the so-called lazy greedy approach. The idea is to use this implicit thickening only for set removal, so when we delete the paths which are already hit, and not for selecting the hitter in the first place. Okay, so what we do is, like before, we extract and store all shortest paths longer than B minus 2D, which we have to do to guarantee global feasibility. When each round, we select the vertex which hits most of these paths directly, so is really on the shortest path. But then, we remove not only the paths directly hit by this vertex, but also the ones which are indirectly hit, so via a detour, in the following sense. So the main idea here is that we can now determine locally which paths are also hit indirectly, And this is, of course, every vertex or every path that you sit indirectly has to be in a d radius around our hitter, okay? Because this is the d2 bound, everything that's further away cannot be hit by our vertex. So we identify all the vertices in the d radius around H, which of course can be done by Dijkstra again or something else. And then, for all the contained vertices, we pick in the shortest path, we look if this vertex is in, and if yes, we remove the whole path. Okay? So you can do this. And this is much, much faster than implicit thickening, of course, because we don't do this whole process of thickening each path. We only thicken a very small subset in each round. But of course, we do not do justice to vertices which hit very few paths in a direct manner, but a lot of paths indirectly, okay? Because we don't count it. We remove it everything in the end, but we don't count it to select. So maybe we select a wrong guys in a lot of rounds. We will see how this performs in the end. The second heuristic we propose is so-called batch computation. The idea is to cut a problem down in sub-instances which can be solved, and then in the end, plug everything together. So to be more precise, we partition our set of vertices into V1 up to Vk, and for every partition, we extract all the paths which are infeasible, which originate in a certain partition. And of course, we can make the partitions as small as desired to make sure this fits in memory. So we compute a hitting set for those, maybe using explicit thickening or whatever you like. And then we make this for all of the partitions. Of course, we ignore the paths which are already hit in previous rounds, and then we aggregate everything into a global hitting set solution. And the thing is, the smaller the partitions, the smaller the computation time, and the smaller the space, but the worse the solution quality. Okay, and the last thing we propose is pruning. Here the idea is to forget about this detail stuff in the beginning. We just compute a global solution for hitting shortest paths, and then in the end we do post-processing and ask ourselves, can we throw out some of the loading stations, still having a detour coverage. Okay, so for all of the hitters, we remove them temporarily from the set, and now we check for the other guys. So we have two paths which are now not really hit anymore directly, but if there are other guys which we can reach via detours, which are bounded by D, we can just forget about this one. Okay, we just throw it out. Okay. And of course, the order in which we consider these loading stations is very important for the quality in the end. So it might be that we consider one, throw it out, but if we would have kept them, we could have thrown out 10 others. So we played around with this. And the cool thing about this is we can tackle really large instances, but the solution quality is kind of restricted to the set we have. So we can just prune out, we don't take new stuff in, which means if the initial solution is pretty tight, we might not be able to gain a lot. Okay, and we also computed lower bounds. I won't go into detail here. The idea is just, if you have heuristics, we want to make sure that we are not too far away from the optimal solution. So we don't know the optimal solution, we compute some lower bounds to which we are going to compare our heuristic solutions, and we made some new lower bound computation which allows us to have better, larger lower bounds, but I won't tell you the details now. Let's come to experimental results. Well, here are the benchmarks. These are all colors of road networks of Germany. So more or less, the first ones are toy instances, just to show scalability. The last one is all of Germany, and we assume an electric vehicle can drive around 150 kilometers, and then we allow a detour bound of 5 kilometers. Okay, so that's the important thing. All others is to show scalability. And we use this explicit thickening algorithm, and we could only compute a solution for the very first, the very small city in Germany. For everything else, you see the space consumption is in the order of a lot of gigabytes, and then approaches terabyte already for medium-sized cities, so this is just not true. Okay, so at least not on the hardware we have. Okay, but using implicit thickening, we see we can get one step further. We can solve one larger instance, but again, all other bigger instances are not tackleable with this. Okay, let's come to the heuristics. Batch computations gets much further, so we can solve Stuttgart, so it's a big region around the city, pretty large, with over 2 million nodes. And we see the approximation factor compared to our lower bounds is about 6, which is quite okay. If you look at pruning, we can solve everything with that, all of the instances we have, because the shortest path cover could be computed for all of those, so we can, of course, apply pruning. And we see the solution quality is worse than for the greedy thing, for the batch computations, for those we could solve. But we can tackle everything, and we say with this delta, we show how much we can save compared to the original thing where detours are not allowed, and we see that we can save up to 30%, depending on the instance. Okay, here's some ICAPS, where you can see in the middle that this red guy remains, but all the black ones around are approved. Okay? And once we have this cover, we want to know where to recharge. And the idea is very similar to the proof I made in the beginning to show global feasibility. We always look at a B-2 long path, and then we just use the loading station which is latest on this path, and we can show that can be very efficiently implemented. It always returns a feasible path, and we have an arbitrary bound on the number of recharging stops, just depending on B, D, and the shortest path length R, which is kind of good if you want to know an upper bound, so you can really be sure to don't go too much, or kind of guarantee that you don't want to have too much recharging stops, and this is also reflected in our results. The average number of loading stations we visit is kind of equal to the lower bound. Okay, and also if you look at the difference, or the distance between two charging stops, we see this is kind of B minus D, which is very similar to what I proposed to you in the beginning. If you drive by a conventional car, you just go around and wait till you're have very small fuel load, and then you just recharge. And it turns out that if you have this kind of cover, we can do more or less the same with our electric vehicles. So yeah, what we've seen is pruning can tackle everything, but other approaches might perform better if we can make them scale better. Yeah, and there are a lot of open things to do, of course, make them more efficient, make them tackle larger instances, maybe incorporate other stuff as well, like traffic volume, route popularity, and so on and so on. Okay, thank you.
Questions?
I probably missed it, but how many charging stations would be required in Germany, and how many did you say in respect to this approach where you said you have a huge number of charging stations?
Yeah, well, so for Germany, this is the last slide here. For the pruning thing, we save about 10%, which, yeah, okay, it's 10%, that's okay, but we think if we will have the greedy algorithm to scale better, if into Germany, we might save even more. So if you look at approximation guarantees for these heuristic, it's a lot better. So if we could get it to whole Germany, we think we could save more. And maybe for pruning, so in a moment we start with this very tight set, we could increase the initial solution for this pruning strategy and then run our post-processing, given a larger degree of freedom to select which might be a good loading station, and we might also be able to improve on this. But at the moment it's about 10% that we can save.
Let's thank the speaker again. Thank you. The second talk of the session will be presented by of the University of Melbourne, and the paper is entitled Towards Next Generation Touring.
Okay, thanks for the introduction. Hi everyone, my name is Kwang, and this is work that is done in collaboration with Jeffrey from IMIT, Christopher and Shanika from Uni of Melbourne. So the topic of this talk is on how we actually recommend and plan tours, in particular trip itineraries for groups of tourists. So before I start on the problem itself, I'll perhaps go through how a person or a tourist will typically plan a tour. So if you're going to a new city that you're unfamiliar with, you might consult some resources that are available online. So you have things like travel blogs. So these are basically blogs that are written by people who have been to certain places. You look at, they recommend about the places that have been to, review about those places, whether it's nice or not, the pros and cons. Or you might potentially go and look at online guidebooks, things like TripAdvisor and Lonely Planet. So what these online guidebooks does is they recommend you individual places of interest, popular places in fact, and things like TripAdvisor, they rank them according to which is the most popular, second most popular, etc. So just by looking at all this, it's possible to get a list of places of interest or POIs then the issue becomes, now you have a list of POIs in a specific city, and how do you actually go about planning a tour or a trip, sort of a trajectory that covers a certain set of these POIs, and which are the POIs you choose. So this is a very time-consuming and complex task, especially for tourists, because from a tourist point of view, there are many considerations that may be on their mind. Like for example, they may have a limited duration for the tour itself. So they could have 3 hours and they need to cover the entire tour within 3 hours. They may have certain preferences to start and near certain places. For example, they may want to start near the hotel where they are staying at. They may want to end at a restaurant where they can have dinner at the end of the trip. And also there are different types of POIs, or rather the categories of POIs. So you have museums, church, and many other categories. And you actually want to plan the trip that is aligned to the interest preferences of these tourists. So this itself is quite a time-consuming task. And one possible solution is you could potentially engage the services of tour agencies or tour operators. So what these tour operators do is they provide you with a package tour. So they give you a list of POIs and they assign tour guides to you. They bring you to this certain set of places. So typically these are popular places. And they typically tell you this tour will start at this time and end at a certain time. So there's a fixed duration. And one important thing is all these package tours are normally catered for groups of tourists. So that is the domain of our work. So we are interested in tour recommendation for groups of tourists. And there's a few challenges to this area. So the problem we are dealing with is both a recommendation problem as well as a planning problem. So the recommendation part comes with the challenge that there are many tourists in a certain group, and each of these tourists will have their own set of interest preferences. And this simple tour example that you can see is just an example of 3 tourists. So each they have their set of interest preferences. But in real life, we are dealing with a lot more tourists, and the interest preferences are not so binary. It's not like simply you are interested in a certain POI category or not. In real life, all of them could be interested in museums, but they could have varying levels of interest in each of these categories. So the issue in our work is now, how do you actually determine these interest preferences? How do you moderate? And how do you represent it for a group of tourists? And similarly, as a tour operator, you are also bounded by certain constraints. You have a limited time for the tour. You want it to start and end at a certain place. And more importantly, as a tour operator, you probably plan multiple tours. So the issue becomes, how do you best assign your tour guides to lead each of these tours? How do you model the expertise of these different tour guides such that they are best equipped to lead different tours? So this is some of the challenges in group tour recommendation, which we hope to address as part of our work. And our contribution is the modeling of this group tour guide problem, which involves recommending and planning tours for groups of tourists, and then assigning tour guides to lead each of these tours. And because this problem is a hard problem to solve, so we try to decompose it into 3 smaller sub-problems, comprising of tourist grouping, POI recommendation, or the trip planning itself, and also the assignment of tour guides to each of these tour groups. And we evaluated our approach against various baselines using a figure data set across 7 cities. So now I'll talk a bit more about the formal definition of group tour guide itself. So the idea is that there is a set of tourists and tour guides for a particular city, and there's a set of POIs in each city. So our problem is to try to maximize this objective function here. And in this objective function, we are interested in a few things. We are interested in the grouping of the tourists into the different groups. We are interested in the POIs to recommend to each of these groups. And in particular, we want to recommend POIs that maximize a certain utility function, which is represented by both the tourist interest and a particular POI popularity. So we want to maximize this as much as possible. And this controlled by a ICAPS parameter that allows us the flexibility to emphasize between the two. And it's not so simple as to recommend POIs. We need to construct this as a cohesive trip itinerary, bounded by the different constraints that we mentioned, a start point, an end point, a limited tour duration. So there's many more constraints involved, which is listed in the paper, so you can take a look at that for more information. And for the right part of the problem formulation, this is where we try to best match a tour guide to the different tour groups based on their expertise. And now I'll go on a bit more about the definitions that we use in our work. So in our work, we actually we try to model the places that a person has gone to based on his or her travel history. So the idea is there's a sequence of travel history, the different places they have gone to, the time they have spent at each place. And also we adopt a simple measure of POI popularity based on the number of times this place has been measured, has been visited. So the more time it has been visited, the more popular it is. And for us, previously we talked about this modeling of interest. So in our case, we model interest preferences based on the amount of time a tourist has spent at the POIs of a certain category compared to the total amount of time they have spent in the tour. So the basic intuition is that the more time this person has spent at a certain POI category, the more interested they are compared to if they spend less time at those places. So that is the intuition. And this representation so far is for one POI category. And in our work, we model it across the different POI categories. So we represent this as a vector, one for each POI category. And similarly for tour guides, we also try to model the expertise of these tour guides. But instead of POI categories, we model it based on individual POIs. And the idea is the more times this tour guide has led a tour to a certain POI compared to the average user, the more experienced this person is. So they have a higher level of expertise. And again, we represent this as a vector, but it's a vector one for every POI instead of categories. So we choose to do it this way instead of for POI categories because we want a more fine-grained measures. So a tour guide may have different varying level of expertise in different POIs, even though they are in the same category. So that is one of our consideration. And as we have mentioned earlier, the group tour guide problem is hard to solve optimally by itself. So our approach was to actually break it down into three sub-problems. So the first sub-problem that we are looking at is the tourist grouping problem. So in this particular problem, we have a set of tourists, each of them have different interests, and this interest we model based on what we have introduced in the previous slide. And now we have a set of interest preferences for each tourist. We use these interest preferences as a feature set, and then we apply the k-means clustering algorithm and hierarchical clustering algorithm to cluster these tourists into different groups. And what we have now is a set of groups of different tourists. And now that brings us to the next sub-problem. Based on each group, we then try to plan the tour, recommend POIs to each of these groups. And we model this problem based on the orientation problem, such that we consider things like the interest of tourists, the popularity of the places, as well as considerations for starting and ending points, and the limited time duration to complete the whole tour. So this is a variant of the orientation problem. And in terms of the interest, we use a group interest that is based on the average of all users within the group. And in turn, that gives us a set of trip itineraries that's recommended to each tour group. And the last sub-problem is the tour guide assignment problem. So now we have a model of the tour guide expertise, which was mentioned previously. And so we are trying to match the tour guide with the best expertise to each of the recommended tour. And this is a one-to-one matching, so now we are assuming one tour guide to one tour group. So essentially this is the overall idea of our breaking up into different sub-problems. And more formally, this is what we are trying to optimize for each of the sub-problems. So for tourist to tour group allocation, we are actually trying to maximize the interest similarity between users in the group. And we do this using k-means and hierarchical clustering. And for the POI recommendation to tour group, this is also the planning of the trip itself. We are actually trying to maximize this utility function of interest and POI popularity. And there's a beta parameter that allows the user to control how much under emphasis on interest and popularity. So for our work, we look at both a 50-50 weightage as well as a 100% interest weightage. And then there are other constraints also, which is illustrated in the paper itself. And lastly, we have the tour guide to tour group assignment, which is essentially a matching problem. So we are trying to match the tour guide with the best expertise to each of the recommended tour group. So, as I was mentioned earlier, a lot of our work depends on the previous travel histories of the tourists. And using this travel history, we determine their interests as well as the expertise of the tour guides. So then the question becomes, how do you actually get this travel history from a tourist? So the idea we had was to make use of geotag photos. So this can be any form of location-based media. What we are interested in is not the photos itself per se, but rather the metadata that's associated with each of it, particularly the lat-long location, the time that this photo was taken, the user who has taken this photo. So it doesn't have to be a photo, it can be a geotag tweet, or it can be a tracking data. And we also make use of semantic data, like a list of POIs. And for this purpose, we look at Wikipedia. So Wikipedia has a list of places of interest for each city. And for each of these POIs, it's actually grouped into different categories. So that provides us with some semantic information of the different categories that the POI will fall into. And each of these POI will have a lat-long location. So now we have this lat-long location for both the photos and the POIs. And what we can do now is we can do a mapping of these photos to the POIs. And after this mapping is done, what it tells us is that it gives us a history of the different places that a person has been to, a tourist has been to, and in particular the POI that they have visited, the time they have visited, and the categories of this POI. And because each of these POI visits are stamped with a time, we are able to order them in the time sequence, and that will give us the travel history of this particular tourist. But however, this travel history might span multiple days, weeks, or even months. So for a different interpretation, we actually break it down into smaller parts so that they are a bit more reasonable. And we break this out based on the time difference of 8 hours. So say for two consecutive photos, if the time difference differs by more than 8 hours, then we'll break them into different travel sequences. And then we use these travel sequences as a ground truth, which we use for our subsequent training and evaluation. Yeah, so the data set we use is the Yahoo Flickr data set, and this comprises 100 million photos. And this is the basic statistics of all the photos that we data mine based on the previous approach that we mentioned. And we are mainly concentrating on POI sequences with at least 3 POIs. So for each of these travel sequences with at least 3 POIs, we do 3 things. So we randomly select 100 users from each city, group them into 5 different tour groups, and then we apply our tourist to algorithm to it. And then for each of the group that's allocated, we then try to recommend trips or tours to each of these groups, and then we measure the performance of each of these groups. And then we try to assign tour guides to each of these tours to see how well they match the tours itself. And we compare it to various baselines. So one is the first come, first allocated baseline, like how typical tour agencies do it. So the first 20 that comes, they'll fit into one group, the next 20 goes to another group, and so on. And we also do a random baseline. And for the recommendation of POIs itself, we compare it to the standard package tours that is currently offered by these online travel agencies. So we compare how well these tours, this POI satisfies the interests of the users compared to our algorithm. And we also compare our orientation problem-based algorithm using the earlier two groupings based on first come, first allocated and random allocation. And also for guide to group, we look at the random allocation. So the evaluation comes in a 4-part section. So one is we evaluate the clustering of the tourist groups. So in this, we are interested to see how similar the tourists are in the groups that are being grouped. So we look at these 3 metrics. One is Jakarta similarity, Tosa similarity, and one is the ratio of users within the group with the same top interest. So the higher these scores are, the better it is. So I wouldn't go too much into the results. You can refer to the paper for more details. But in this case, the one that we propose, K-means and hierarchical clustering outperforms the 2 baselines. And similarly for the recommendation of the POIs or the tours itself, we are interested in the three metrics. So one is the total interest of the entire tour, that is the interest satisfaction to a tourist, and also a maximum interest and minimum interest for the tourists in that tour. So the idea is that this maximum and minimum interest indicates the happiest and unhappiest tourists. And we are interested in the unhappiest tourists because the unhappiest one is more likely to write a negative review. So we want to maximize, we want the algorithm that is able to maximize these scores. So again, I will not go too much into the details. But in all the cases, our proposed algorithm outperforms the baselines, and the results, the improvements are statistically significant. And lastly, for the guide to group, we also look at the total expertise of the tour guides. So again, it outperforms the baselines. And as an overall evaluation, we look at this objective score, which is based on our original problem formulation. And the idea here is we are doing sort of a parameter analysis to see that if we change the alpha value, does it change the performance of our algorithm compared to the baselines? And also the result shows that although the exact score changes, but in all cases, regardless of the alpha value, it still outperforms the baselines at the same alpha value. Yeah, so in conclusion, in this work we have formulated this group tour guide problem, and because this is a hard problem to solve, so we break this down into 3 smaller subproblems of tourist grouping, POI recommendation, and tour guides to group allocation. And then we evaluated our approach on a filtered data set of 7 different cities. So there are some future work that we hope to embark on. So currently this work is based on a single mode of transport or walking. So in future we hope to extend it to multiple modes of transport, maybe walking, then cycling, then public transport, etc. And currently we assume that it's divided into 5 groups. But in real life there is a competing demand. Tour operators, we want as many users in the group as possible to maximize their profit. As a tourist, we want as small a group as possible to maximize the attention you get. So we hope to find some way to model this difference and come up with a good model to resolve this. Yeah, so that is some future work we are looking at. And with that, I've come to the end of my presentation. Thanks for your time.
So what is interesting for our community is probably the planning aspect, so the second aspect. And I also looked into this problem, so it's got this orienteering problem, tourist visiting problem, and usually it's with public transport. So where you have edges that vary with the time when you are there. Because of the time windows, you may not make it to the London Eye because it takes too long. So do you have anything towards solving this problem? You just do a mid-formulation and then try to solve the mid-formulation, because there is a traffic salesman in there. It's a really hard problem, and it's not so easy to solve that with mid-technology. Have you looked at it? So we tried with Monte Carlo search, but it would be interesting how you would actually do the routing.
So I think what you're referring to is the orienting problem with time windows. So
yeah.
for now, we are looking at the vanilla orienting problem. So we don't consider the chances of missing a transport.
Okay.
And another thing is our problem now is based on walking within a city. So the time needed to get from one place to another is based on walking speed. To address your question about the complexity, in this case, we are using it as an integer program. We also develop a web application, and in the web application, we are trying to get a faster performance. So we actually use an n-colony optimization system. So it's a genetic algorithm kind of system. So that allows us to get solutions that are not so optimal, but obviously sufficient for the purpose of tour recommendation. And the good thing is we can get a solution within 1 second. Compared to our integer program formulation, which takes, for some larger cities, it takes more than 10 minutes, for example, to get a solution. So that wouldn't be good enough for web application. So hopefully that answers your question.
Yeah, at least it opens your bit on what technology is inside.
Okay. Thanks for the question.
I have a question. When you showed the choice preferences, you looked at the past histories of what it is. I wonder if someone visits Melbourne, maybe they do several different tours, and you recommend you should have a tour with lots of parks, as a legitimate parks tour. And then they want to do something else. So preferences can change based on what you've done. Does the question make sense?
Yeah, it does. So that there's So one which we have not addressed in this work. So the idea is that interests may change over time. So currently what we are looking is sort of a static representation of interest. So that could be one thing we look at in the future. In fact, there is one later work that we are currently working on. Is we try to model this interest such that places that the person has visited recently has a bit more weightage compared to places that they have visited, say 10 years ago or 5 years ago. Yeah, so we are in the midst of trying to do something like that. Thank you.
Let's thank the speaker again. The final talk in the session today is by Christian entitled More Shuttles, Less Cost.
Thanks for the introduction. The question we had is create a warehousing system that's capable of moving all the items stored in the system simultaneously, individually, and without any preparation time. How would we use such a system efficiently? Very nice. How could such a system look like? I think if not most of you know Amazon Robotics, formerly Kiva Systems. There you have racks and you have robots, and the robots go to the racks, pick up the rack, and move it where it has to go. Now you could imagine that each rack has its own Kiva robot. You might say, that is incredibly inefficient. Why would you need so many robots? And you're right. You're right in the same way that it's totally inefficient for each person to own a car or a personal computer. I mean, like 2 hours on a mainframe should be totally enough for everyone, right? And we know, of course, that that was true once, but as time passed, computers became cheaper, cars became cheaper, and now we are very glad that we each own one. And I believe the same will be true for robotics. So Kiva robots will become cheaper, or there will be other systems around that allows this kind of system. And the real question is, of course, is it worthwhile to build such a system? Now, as a use case that we look at, we have the early baggage store of an airport. When you will be leaving ICAPS in the next days, you will go to the airport, you will check in your luggage, and your luggage will be placed in such a blue baggage tray. I don't know if you can recognize anything, but what you would recognize, if you would recognize anything, would be baggage trays and a piece of baggage in one of the trays. And these trays are placed on conveyor belts, and that's how your baggage is transported within the airport. But what happens if you arrive early or your flight is delayed? Then your baggage has to be stored. And today, this is done in this early baggage store, which consists of a huge conveyor belt moving the baggage in cycles, so the baggage moves all the time. And there is a junction that can detect if the baggage that should be removed passes this junction, and if the wireless connection still works, but I think it's not part of it. And if your baggage is ready to be loaded, then it is requested and loaded, removed from the early baggage store and loaded onto containers that will eventually go to the airplane. Now, we don't simulate this conveyor belt in the use case. We simulate the system I just described in the question I asked. We place each piece of baggage on its own robot and, well, try to create an efficient early baggage store using these robots. Before I go on, I have another question to ask you. We simulated these 3 layouts. The bottom layout is basically what we would use today. Every third column is kept empty, so we have a column to move in, and in the top 2 layouts, these columns are removed mostly, so as to allow a denser storage capacity, a higher storage capacity. But of course, if we want to access a piece of baggage, and it isn't connected to one of the roads directly, then we have to move other pieces of baggage before we can access it. And my question to you, and I will have a word at the end of the talk before I give the results, is which of these layouts is the most energy efficient one? Obviously, the bottom one uses the most space. Actually, it has 55% coverage of robots. The one in the middle has 87% coverage of robots, and the top one has 82% coverage of robots. Now, the system we are looking at consists of a rectangular workspace divided in rectangular cells. Each of these blue boxes is one cell, and each cell may hold one robot, which we encode as red cells. And each robot is allowed to move to its adjacent 3 cells. And, well, all the robots that can physically move at the same time are allowed to move at the same time in our system. So all the motions depicted by arrows in this slide can be executed simultaneously. The task that we want to solve is, well, we want to build an in-house logistics storage facility. We want to store many items in this airport application. We have 2,000 design capacity of 2,000 pieces of baggage, so 2,000 robots. Given this design capacity, we want to minimize the size of our warehouse. Obviously, we also want to minimize the number of motions so as to minimize the energy requirement. And all this, of course, still has to be fast enough that when your flight is announced, the baggage can travel to the aircraft and be loaded and not end up still being at the early baggage store when you are long gone. The input is unordered. We don't know when you will arrive or if your flight is delayed, so we have really no clue in which order the baggage arrives, but the output is sorted by flight in general. Of course, there can be multiple flights be requested at the same time, but in general it's ordered by flight. Which means we have a storage and sorting task. The sorting can in principle be performed at 3 times. We can take our unordered input and place it on the right position to have it sorted in the store. Each item can move all the time, so we could try to sort it while it is being stored, or we can store it chaotically and then sort it within the output operation. And each of these possibilities has its advantages. What we chose is option 3, simply because, or the one main reason why we did this is because flights can be cancelled or delayed. We really don't know the order of the flights in which they will be requested, or if they will be requested at all. Of course, if the flight is cancelled, then it might be moved some other way. So that's the reason why we sort in the output operation. The model we use to perform the planning task is a simple grid graph. Each cell gets a node, and the nodes are connected by the allowed transitions. And for each shuttle that we have, for each robot that we have, we place a panel on this node. And because we store the items chaotically, we can throw away all the other information for the time being. We treat this as an unlabeled function problem. And now we have to solve 2 tasks. To use this system as a warehousing system, we have to provide an input operation and an output operation. And the input operation, what is an input operation? An input operation is actually, in an input operation, I don't want to get a robot to get someplace. I want it to disappear from someplace. I want it to disappear from the input location so that I'm able to put another item on the input location. And in this example, we have chosen T as a storage location, S is our input location. We want to clear S and occupy T. For some reason, we have chosen T. That probably wouldn't make sense here, but it's to illustrate how the method works. Because we will use this method not only for the input operation, but also for the next strategy, planning strategy that I showed. And what we do is we find the shortest ST path, and then very simply move each of the shuttles on this path to its predecessor. So the last shuttle on the path moves to the end of the path, the shuttle before that moves to the previous position of the last shuttle, and so on. I have a small animation. The important thing really is that we keep all three cells at the same position where they currently are. So the two, or if you look at the position of the three cells in these two columns, you will notice that the only three cells that will change now are S and T. Their occupancy is swapped. And that looks like this. We move these shuttles like so, and then the one shuttle on the path moves 2 spaces, and the position of the three cells doesn't change. The pebble configuration is the same before and after the operation, except S and T. And the cost for this operation is equal to the path length, because each edge is exactly used once. The second idea, the more interesting one, is now defined as follows. We use this technique, for example, if you want to access a shuttle and we want a road which we can use to travel along. In this case, the hatched cells, X, should be cleared. We want to use this area as a road. And the cells, the three cells is the cell F, and we notice that 2 cells, F and X, are overlapping. That is okay, because we want to make sure that after our operation, these 2 cells still are free. What we do is we compute minimal cost matching between X and F, between the cells that we want to clear and the 33 cells. And this matching, a minimum cost matching is an empty set that doesn't help us very much, so we compute an inclusion maximal, a cardinality maximal matching with minimal cost. And then we perform a push move along each of the paths, or along the shortest paths between each path in this matching. And that clears X, obviously, because, well, we have performed a push move and the source gets cleared by the push move. And we notice that the cost, because the cost for a push move is equal to the path length, independent of the question how many shuttles are on the path. And the configuration isn't changed except for the destination node of the push move. This works in any order. We don't need to worry about in which order we perform the push moves. And the cost of this evasive motion, of this clearing motion, is equal to the cost of the matching, because for each element of the matching we perform such a push move. And it can be shown, and I'll have to refer to the paper, that this operation is the best we can do regarding this unit cost model. It's the lower one. Now if we want to remove these 2 shuttles marked by X, the flight for these shuttles is now announced. We want to access these 2 shuttles. What we do is we find a path connecting these 2 shuttles with the output. Then we disable these cells because our clearing motion can change the location. At this point, the unlabeled pebble motion doesn't really capture the problem anymore, because we have to keep X at its current position to use this as a road, which means in our model we remove the arcs in this graph. Then we compute clearing motion for the rest of the shuttles on the path, which gives us a trivial output operation for these 2 shuttles X. They are placed on a road leading to the output, not containing any other shuttles, so perfect. As I said, we have different possibilities to lay out our workspace using these operations for inputs and outputs. And I already showed them to you. The main difference is we have one version with opposite side input and output locations. They are marked by I and O in output. One version with input and output locations on the same side of the storage area, and this naive layout. And now I would ask you who thinks the best energy efficiency, the least amount of motion per piece of baggage is in the top layout? Raise your hands. Top layout is the best. Okay, who thinks the middle one is the best? Okay, and the lowest one? And the rest is, okay, hoping that we won't lose that baggage on the way home. Okay, well, I have to admit, some of you seem to have a better intuition than I did. I was pretty convinced that the lowest layer would have the lowest energy requirement, but in fact, we have performed 2 sets of simulations, one for the maximum load day to verify that the speed is sufficient, and one for the average load day to verify that, or to get an idea about the energy requirement. And the middle layout has the lowest energy requirement for both the maximum load day and the average load day, and has the highest space utilization, 86.7%. There's something given here, the input queue length. When a piece of baggage arrives that cannot enter the storage at the current time, it is placed in an input queue that is also done with the current system, because you have this conveyor belt, you want to enter it, and if there is on the junction where you enter it, there's already a piece of baggage you can't enter, you have to wait. So the length of this input queue gives sort of an idea regarding the speed of the system. That is not as good as in the other system, but it is good enough. We have verified this with the practitioners using the system today, the baggage storage system today, and the input queues are longer than that. So it works, and yeah, I was surprised that both energy efficiency and space efficiency go hand in hand. So in conclusion, this approach, placing each piece of baggage on its own robot, has a huge benefit on the space required. Today's system could be cut in half regarding size. The distance we travel per piece of baggage is 3 orders of magnitude below the current system. Today, a piece of baggage travels approximately 25 kilometers, and with this system it's 20 meters, so 17 on the average day. So it's a huge gain in both energy and space. And we also performed these simulations with 2 aspect ratios each, 1 by 10 and 1 by 6, which corresponds to today's system layout, and the results are pretty similar. Thanks for your attention, and yeah, thank you.
Time for questions?
In the layout you showed, only the middle one has both the input and output on the same side. Maybe the energy, the distance travel is because of the reason or not?
Yes, indeed. The problem with warehouses is that you have to design them to be large enough to hold the maximum capacity load. But usually you only utilize them like half of the capacity. We all know this from trains. On rush hour they are more than full, but on average there aren't even all seats taken, so the design capacity exceeds the average capacity by far. The same is true for this warehouse application, and indeed that was the idea behind this design, to bring the input and outputs closer together so that in the average load day we can exploit this fact that the store isn't full, that it behaves somewhat as if it would be a smaller warehouse, which saves traveling distance. Exactly.
With the random storage, it's probably very unlikely, but when you are removing items from the mass and you hold the items that you want to be removed in a static location, is it possible to create like a perimeter around the useful spaces that you would need to kind of rejigger things to get a path?
It is, in fact, one has to be careful when creating multiple output, or using multiple output locations at once. which we solved by associating an area of the warehouse with this output location so that it can interfere. Whereas regarding the output of only some items, here we could, for example, have the middle column. We would want to remove the middle column, we would disable the middle column, cutting the graph essentially in half. It would fall into two connected components, but it wouldn't, in this example, really matter, because that would mean that we want to remove the whole middle column, which we still can do. So the only thing we would have to guarantee in this case is that we don't want to have an input operation at the same time, but this is also the reason why we have in these layouts a lane above the input locations that allows us to move above any disabled area. But in practice, if your system is the only system that accesses this graph, then it is pretty, care has to be taken, but it is easily doable to avoid these situations.
Well, let's thank all the speakers of today's session.